Welcome to the Future Lab. I'm your host, Matthew. Today, we're exploring a pivotal shift in the process and energy industries, the rise of unmanned and autonomous systems. It's a field ripe for transformation, and we're going to delve into a recent research paper that highlights both the potential and the considerable challenges. These sectors are facing some serious headwinds: a shrinking pool of skilled workers, a growing emphasis on sustainability, and the critical need to address climate change. Can automation alone solve these problems? That's the big question. A recent research paper suggests the answer might lie in unmanned and autonomous systems. It's a bold vision, and today, we'll explore what that vision entails, where we currently stand, and what hurdles need to be overcome to bring it to fruition. We'll start by looking at the main factors driving this trend toward autonomy in process and energy. Then, we'll deep dive into the research itself, examining both the high-level results and the more intricate technical details. After that, we'll explore the real-world applications, the broader impact on these industries, and finally, what the future holds for this exciting field. So, let's start with the driving forces behind this push for autonomous systems. What are the key challenges facing the process and energy industries today that make autonomous systems such an attractive solution? Well, the paper points to a perfect storm of challenges. We have a declining number of skilled workers, increasingly stringent regulations around sustainability and safety, and a pressing need to decarbonize. All of this creates a compelling argument for adopting technology that can help us manage complexity and reduce our reliance on human expertise. Exactly. And it's not just about cost savings, it's about ensuring safe, reliable operations, particularly in environments that are hazardous or difficult to access, like offshore platforms or remote gas fields. The potential for enhanced safety and productivity is a major motivator for this shift. Absolutely. The increased efficiency, safety and resilience offered by autonomous systems is a compelling case for their adoption. But before we get into the technicalities of this research paper, let's briefly recap the key findings before we dive deeper. The transition towards widespread autonomy won't be seamless and involves a more holistic approach that includes rethinking plant design. That's a perfect segue into our next section. We'll now dive deeper into the research itself, focusing on the key findings and methodology. We'll unpack how the researchers approach this problem and the technical details behind their proposed solutions. So, let's turn our attention to the research paper itself. The title is quite descriptive: Unmanned and Autonomous Systems, Future of Automation in Process and Energy Industries. It was authored by Francesco Burrison, Marta Zagarovska, and Mehmet Merkangos from Imperial College London. The overarching goal of this research is to investigate how autonomous systems can help address the major challenges currently facing the process and energy industries. And this research is vitally important because, despite significant advancements in automation, these sectors still heavily rely on human expertise, creating both operational bottlenecks and vulnerabilities. This research seeks to identify how to automate those currently human-dependent tasks. The aim is to improve safety, sustainability, and the overall resilience of these crucial industries. The core idea is quite straightforward: to identify which operational tasks in process plants can realistically be automated using unmanned and autonomous systems. This isn't just about replacing humans with robots, it's about understanding the nature of the tasks themselves. Exactly. And their findings highlight two particularly crucial aspects: the need for adaptable systems that can cope with the inherent dynamism of industrial processes, and a deep understanding of the different layers of complexity that can impede the successful implementation of autonomous solutions. The researchers didn't just identify challenges, they also categorized the complexity involved. They broke it down into three key areas: the complexity of the plant and process design itself, the complexity of plant operations, and the complexities involved in the interactions between the plant and its surrounding environment. This layered approach to understanding complexity is a significant contribution. So, we've established the study's goals and high-level findings. Now, it's time to delve into the specifics. Let's explore the methodology, the nuts and bolts of how the researchers conducted their investigation and what their approach entailed. Let's get into the methodology. The researchers started by meticulously analyzing the various tasks involved in running a process plant. They didn't just look at the big picture, they broke down the tasks into three fundamental categories: manual labor, sensory input, and cognitive input. This breakdown is insightful because it helps to clarify which aspects of plant operation are currently reliant on human capabilities and therefore are candidates for automation. Can you elaborate on how this categorization informed their analysis of automation feasibility? Precisely. By categorizing tasks, they could then evaluate the feasibility of automating each category using existing and emerging technologies. This wasn't just a theoretical exercise, they mapped each task to potential autonomous system realizations. The paper explores different levels of autonomy, ranging from remote operation, where human operators are off-site but still actively involved, to fully autonomous operation, where human intervention isn't required at all. This is a nuanced view of autonomy, reflecting the spectrum of possibilities. This is where the complexity analysis becomes critical. The researchers identified three main dimensions of complexity impacting automation: plant design, plant operation, and the plant's interaction with its external environment. Can you expand on the significance of this three-pronged approach to complexity? That's a really insightful point. By examining these three interacting aspects, the research moves beyond simplistic assessments of automation feasibility, highlighting the many interdependencies involved. It's not just about the technology, it's about how the technology fits into the larger system. This three-dimensional complexity view is one of the paper's key innovations. And what about the challenges they encountered? What obstacles did they highlight as potential impediments to achieving higher levels of autonomy? Indeed, the paper's comprehensive approach is a major strength. They not only mapped various tasks to suitable technologies but also candidly discussed the challenges involved. The need for adaptable, model-based solutions stands out as a key challenge. The dynamic nature of industrial processes requires systems capable of continuous adaptation and learning. Precisely. And the researchers stress that simply swapping robots for humans isn't sufficient. Achieving higher autonomy requires a truly systemic approach, integrating technology, plant design, and operational procedures. It's a holistic view that underscores the complexity of the undertaking. This sets the stage for our discussion of the real-world applications of this research in the next section. So, we've covered the methodology and the key insights from this research paper. Next up, we'll explore how this work translates into real-world applications and the far-reaching implications for the process and energy industries. Now, let's move on to the practical implications of this research. Where can we expect to see the most immediate impact of these advancements in unmanned and autonomous systems? The paper points to several key sectors. Offshore oil and gas operations immediately spring to mind. The high costs and inherent risks associated with human presence on offshore platforms make autonomous systems particularly attractive in this environment. Absolutely. And we're not just talking about oil and gas. Remote facilities in general, think remote refineries or power plants, stand to benefit immensely from increased autonomy. The ability to operate these facilities with minimal on-site personnel offers significant advantages in terms of safety and cost-effectiveness. That's true. The researchers also highlight the potential benefits for large-scale, relatively low-risk plants. Think about industrial gas production. Many of these plants are already operated with minimal human presence. Autonomous systems could further optimize these operations, improving efficiency and lowering operational costs. So, it's not just about specific locations, but also about optimizing existing operations and processes. This research underscores that designing plants with automation in mind from the start is crucial for maximizing the benefits of autonomous systems. Precisely. This is a significant contribution of this research. It provides a framework for designing and implementing autonomous systems that goes beyond the technology itself. It emphasizes the importance of a holistic approach, integrating technology, operations, and, critically, plant design. Let's consider some concrete scenarios. What kind of real-world improvements might we see as a result of wider adoption of these technologies? Exactly. Imagine an offshore oil platform operating smoothly and safely with minimal human intervention, reducing risks and operational costs significantly. Or picture a remote hydrogen production facility operating flawlessly, irrespective of weather conditions or other external factors. This isn't science fiction. This research shows us how these scenarios are moving closer to reality. This research really pushes the boundaries of what's currently achievable in terms of automation. The key takeaway is that a successful transition to more autonomous operations in the process and energy industries requires a focus on addressing the complexities inherent in these systems and adapting our automation solutions to these dynamic environments. This leads us naturally to our concluding remarks, where we'll summarize the key findings and look to the future. Before we move on to the conclusion, what is the main significance of this work regarding plant complexity and its adaptation to dynamic environments? To summarize this section, the potential applications are wide-ranging, spanning various sectors and operational contexts. But it's not just about replacing humans with robots. Success depends on a holistic approach that considers the complexities involved and anticipates the dynamic nature of industrial processes. This leads us nicely to the conclusion, where we'll summarize the episode and offer a forward-looking perspective. Let's wrap up this fascinating discussion on the future of unmanned and autonomous systems in process and energy. To recap, today's episode has centered around a research paper that explored the shift toward increased autonomy in these vital sectors. The study began by systematically categorizing the various tasks involved in operating a process plant, breaking them down into manual labor, sensory input, and cognitive tasks. This provided a framework for assessing the feasibility of automating these tasks using existing and emerging technologies. A key finding was the importance of adaptable, model-based solutions, underscoring the dynamic nature of these industrial processes. The researchers also highlighted the need for a more holistic approach, considering the complexities of plant design, operations, and the interactions between the plant and its external environment. The researchers concluded that achieving higher levels of autonomy requires more than just technological advancements. It necessitates a fundamental shift in how we design and operate process plants. This involves significant changes in both operational procedures and plant designs themselves. Looking ahead, what are the next steps in this field? Based on this research's conclusions, the paper points to several key areas for future research. The development of more adaptable algorithms capable of handling the dynamic behavior of industrial processes is clearly paramount. Designing plants from the outset to support higher levels of automation is also critical, and I would add that a deeper understanding of human-machine interaction in these increasingly autonomous systems is crucial for ensuring safe and efficient operation. We need to understand how to optimally integrate human expertise with autonomous systems, avoiding the pitfalls of automation bias and ensuring smooth collaboration. That's a really valuable point. It's vital to consider how human operators can effectively supervise and interact with autonomous systems. It's not simply a question of replacing humans, it's about creating a more efficient, synergistic partnership between human expertise and automated intelligence. So, in closing, the path to widespread autonomy in process and energy demands a holistic approach, encompassing technological advancements, design innovations, and a deep understanding of human-machine collaboration. It's a complex challenge, but one with potentially transformative benefits for these industries. Thank you for tuning into the Future Lab. As a final note, I want to point out that this episode's script was AI-assisted, a testament to the very technologies we've discussed today. We hope you found it insightful. Please share your feedback and let us know what you thought. You've been listening to the Future Lab. Join us next time for another exploration into the fascinating world of AI and its impact on science and industry. Until then, stay curious.